Welcome to another special episode of the Space Times Podcast. As always, I'm Paul Mayer here with Harrison Lambert, and today we are ecstatic to be able to welcome Patrick Haddix here from Samara Aerospace. Pat, thank you so much for joining us. Welcome to the show.
Thanks for having me. Stoked to be here.
Yeah, so I mean, there's been a lot of progress that you've been making. You've been absolutely crushing it at Samara and everything that you've been working on. I'd love for you to just really quickly sort of bring us and the audience up to speed. 1,000 yards, couple of sentences, quick picture. What are you doing at Samara Space? What are you building at Samara Aerospace? And where are you currently and where are you going?
Oh man, in a couple of sentences? Can I use a few dozen sentences? Yeah. No, it's helpful to establish a little context because we're doing things a little differently than other space companies. So, yes, I'm the co-founder and CEO here at Samara. Co-founded with my very good friend Vedant, who I met in grad school at the University of Illinois. I got to watch him develop some groundbreaking new satellite control technology while I was over there, and we saw the commercial potential of that sort of breakthrough. So we decided to build a company around it. So at its core, Samara Aerospace is a satellite bus manufacturer. There are quite a few out there nowadays, but we're doing things differently. Our bus is built around a fundamentally new way to rotate satellites in space. Traditionally, satellites are rotated, to make sure they're pointing in the correct direction using a series of spinning flywheels known as reaction wheels, oftentimes control moment gyros as well. These have a number of sort of setbacks involved with them, including vibrating your satellite, which is really bad for sensitive optics. They have a very high failure rate as a mechanical moving part, and they are big, heavy, and expensive. So what we do instead is embed actuation right into the hinges of our deployable solar panels. This system is called MSAC, which stands for Multifunctional Structures for Attitude Control. This is the core invention that was developed and patented by my co-founder. This allows us to vibrate our solar panels in little circular patterns, giving us the same rotational effect as a series of wheels without flying the extra mass. With the added benefit that our system is also performing active noise cancellation, exactly like a pair of noise canceling headphones. Any disturbance on our satellite, it is actively canceled out with an equal and opposite vibration of the solar panels. So we're creating a slimmer, lighter, more agile satellite platform with orders of magnitude more pointing stability, enabling sort of the next generation of satellite optics. And overall, just kind of making it cheaper and easier to get to space.
Awesome. Thank you so much for that 2-sentence overview. So for all of our viewers here and all of our audience who are not watching this interview on YouTube but are listening on some of the podcasts, Pat's background is cleverly an overlay of the entirety of the is that the Hummingbird set that you've been working on?
Yeah.
It's an overview of their first platform that's going up, and you can see it is a flat sat. There's no central cylinder. It is volume and quite clearly very mass efficient. And so just for some orders of magnitude here, because the sheer impact of the control benefit that you're offering, I think can potentially not land with somebody that you're describing this to. But like the sheer impact of being able to 1-for-1 replace the momentum wheels means that you're saving 100 kilos throughout the entirety of a MEO or a GEO satellite, something to that order of magnitude. Is that sort of a fair ballpark to talk about here?
Yeah, I wouldn't even overshoot it like that. I mean, on a 200 kilogram satellite, you're looking at saving, 15 kilograms if you just leave the wheels at home. But that is a 15% increase in your sort of mass efficiency of the system.
Absolutely.
There are a few things to note that might emphasize the benefits more so than just quoting stability numbers. For one thing, we are the only system that is addressing the issue of scaling power. When you want to create a giant satellite, creating a lot of power, you need a big solar panel, and it's going to be a giant, flimsy structure hanging off the side of your satellite, and that is extremely hard to rotate. Um, so if you need to control a big, large structure, we're the only control system that is distributed throughout that structure and actually makes it easier to point the more mass you add to it, because every time you add more mass, you're adding more control. So um, as people talk about some, frankly, a little hyperbolic concepts for massive power production in space, I am actively creating a solution that will allow them to maintain control of such a large structure.
And does
yeah.
everything scale up with the solar arrays? Because I know you have a 2-panel, 3-panel, 4-panel, I believe. And you're saying that the larger solar panels generate more power. Do you also get higher command authority? Do you get more payload mass that you can carry to orbit?
No, it's so the payload will always depend on, how many panels you have, what kind of launch slot you have, on what kind of launch vehicle. But the point I'm trying to make is we scale power and agility in the same direction. Every time you redo the design of a satellite and you need more power, you put bigger panels on. Now your power engineers have to fight your attitude control engineers or your GMC engineers that are like, oh my God, okay, now I have to resize my reaction wheels to make this system work. And it's just everything's so interconnected. It's a lot of fighting requirements. With us, they should be sort of, they scale in the same direction. So you can get more power without enraging your other engineers.
So you're taking what was previously an inverse correlation and you're making that a direct correlation.
Yes. Now
Awesome.
there's a limit. At some point, you're just going to be maintaining agility as opposed to adding it. Of course, you're not going to get infinite rotational speed from a gigawatt solar panel, but yes, it's adding the ability to control a large structure, damp out all of the advanced second order effects, flutter and stuff that's going to propagate through a large structure.
Awesome. And so you mentioned earlier that, you're looking at roughly about a 15 to 20% mass savings just leaving the momentum wheels at home. So if we're dealing with a MEO or GEO bird, or if we're dealing with a bird that's closer to like 500 kilos in size, that's roughly 100 kilos of mass savings there. But the key thing that I want to highlight here is that the fact that you're leaving the momentum wheels at home, the fact that you're leaving that hardware at home allows for the entire bus itself to be redesigned. So tell us, what is the mass profile of your Hummingbird sat?
So the Hummingbirds we're planning for about 100 to 500. We have line of sight to like a 650 kilogram structure. And that's total mass, including the payload. So Hummingbird, we're trying to make it very modular and configurable in terms of power and control. So you can choose how many panels you want on the satellite, which will, eat into your payload mass and volume to an extent. But that's the range we're targeting. And then we have a little longer lead on our scaled up version, which we're calling Kite, also named after a bird. That's basically same thing as a Hummingbird, just scaled up to about 2 tons. And that'll be sized for like the Cake Topper or the Falcon 9.
Is there a reason to create a whole new class out of it if it's effectively a bigger Hummingbird?
Yeah, because the fundamental, the payload plate, for those on audio can't see me pointing to the stuff behind. The payload plate will have to get sized up. We'll probably increase our power control system to enable the larger solar panels to push more current through the satellite. So some things will need to be sort of revamped for a larger system.
Gotcha.
Awesome. And because you're going with a flat sat approach, because you don't have a central cylinder, and because your bus is so much more mass efficient, what's the effective, I'll say, like mass savings or effective mass comparison, sort of like pound for pound here? Because the saving the 15% just by leaving the momentum wheels at home, you're able to redesign the Hummingbird. You're able to redesign your satellite bus effectively from the ground up, centered around your control solution centered around the MSAC. So, what is the effect of like, okay, great, our Hummingbird sat is going to be at the 300 kilogram solution. That's going to provide the same capability as with a central cylinder bus, something that would be in the 1,000 kilogram solution. What sort of comparison pound for pound can you provide in that capacity?
Yeah, there's not that's actually not the selling point we're usually going for. What is attractive in terms of just mass efficiency? So I think the most SpaceX has ever launched in a single Falcon 9 is 28 Starlink satellites stacked, and that is mass constrained, not volume constrained. And if you look at the pictures of the stacks of the Starlinks, you can actually see the reaction wheels off to the side. They are kind of a limiting factor in how thin you can make those satellites. But if you can shave 15% of your mass off your each satellite, now maybe if SpaceX were to adopt this technology, they could put, I don't know, 33, whatever 115% of 28 is. You can fit more things into a launch vehicle that way. But our selling point is less so the mass efficiency and sort of the step change in performance that we enable. Most satellites in orbit are now flying optical communication terminals, i.e. Starlink, and there are a lot of people going after that higher bandwidth. The limiting factor for how much data you can put through one of those lasers comes down to the frequency. And the reason we use such a low frequency laser, it has to do with beam width and how much power you have to pump into this thing and everything. If you want to increase the frequency and therefore increase the data rate of these communication systems, you need basically the beam width goes down, and you need a more stable platform to bolt these things to. So we're actually working towards developing partnerships with these optical terminal manufacturers to create systems that can be higher performing if only they were connected to a more stable platform.
Yeah, and can you real quick go over kind of the pointing capability that you do have, because it's really impressive, the kind of pointing accuracy and slew rates that you're able to achieve.
Yeah, and this is where I try not to get too technical, but there's a kind of a fundamental limit when you're pointing with reaction wheels. Not only are they shaking your satellite. So when you're talking optics, you're talking like, taking a picture of something on the Earth from 300 miles in the sky. The wheels are vibrating a little bit, but when you zoom in that far, that turns into a blurring effect on your images. Same thing with, pointing a laser. Wheels are going to limit you in that regard. We're going for about a 1,000 times greater pointing stability. Generally measured in milli-arc seconds or, nanoradians, whatever you have. It comes down to the angle. If you are focused on a spot, what's the angle that you're going to kind of bounce around that spot?
Yeah.
So that's what we're talking about here, about 1,000 times increase in that pointing stability.
And that's a really impressive number, because there are not a lot of satellites that can achieve that. You're getting to the scale of James Webb Space Telescope, which is a huge imager that needs to remain very steady. And as you point out, optical terminals is definitely a key market for stable platforms. Are there other markets that you're looking at? Because I know like infrared imaging is really important for things like missile defense, which is a growing market recently, as well as any other imaging kind of applications.
Yeah, it's mostly optical. So the ones who are going to see a big benefit are the imaging satellites and the telecoms provider, people transmitting a lot of data. Something we are personally going after soon is I say soon, like 2028. We want to start deploying and operating our own satellites. This will revolve around radio frequency sensing. Because another limiting factor to the kind of signals you can detect from orbit is how big of an antenna aperture you have. But once you start deploying antenna apertures in space, you have all these other effects. It's, again, flimsy. It has flutter. Every time you bump your satellite to try to point at a new target or thrust, you're inducing this flutter in that big deployable antenna. And that's going to blur your ability to detect super weak signals. With us, we are constantly damping out any vibration, any flutter in our antenna, which happens to be integrated on our solar panels. And we can even statically correct for misalignments post deployment to make sure that thing is shaped exactly how it needs to be and no mechanical disturbances show up and blur your signal. So that's another area we are absolutely focused on.
So you're talking about putting your MCAS technology into like a synthetic aperture radar boom?
No, we're still targeting. It just integrates right into the hinges of our solar panels. But your panel design and put some patch antennas on the reverse side. So that's something not a lot of people do. It's been done before, but when you're transmitting, it does generate a lot of heat. And as I said, static misalignments after deployment of a panel, things get misaligned. So our tech actually makes it make sense for us.
Congratulations on your $10 million seed raise. That is a huge accomplishment, especially in the market in which you were raising. It's been effectively sort of uphill sledding for a good little while. And you managed to come through and do it and absolutely knock it out of the park. $10 million at the seed round is a very lucrative raise. So I'd love to hear sort of your take on everything, where you sort of what the terms are, where the company currently stands, and what the goals and milestones are for the deployment of this initial capital.
Yeah, thanks. No, we're stoked that we hit that milestone. Yeah, little backstory there. We closed the pre-seed round last year, used the funding to deploy our first hardware to space. So what actually kicked off our seed round was how quickly and effectively we built and delivered and integrated that on-orbit demonstration of our MSAC hardware. So Impulse Space, who is the host of our satellite, actually referred Valerian Space Ventures over to us. We were happy to kick things off early with them. And they sort of preempted the seed round. We targeted an $8 million raise. We put in the term sheet that, the ability to stretch that up to 10, and good thing we did, because we ended up having to turn some investors away at the end. So, we're really stoked. The capital allows us to grow our team. We have a massively oversized facility here. When we started the raise, we had 1,000 square feet per employee, which is too much. So now we get to hire like crazy. We're going to put our first Hummingbird satellite in orbit in 2027. We have a launch booked for that summer. The big milestone of the raise is just to get that thing built, delivered, and operated in 2027. Of course, next step for me is Series A raise. We're likely to kick that off this year.
I wanted to ask kind of what you're doing with the seed round. I know you said you're planning to deploy the first Hummingbird satellite. Are there still goals that you're trying to achieve out of Cicada? I know you've made contact with it. The testing seems to be ongoing.
Yeah, we're still, and I'll have to be careful about
just that,
because all this gets filtered through Impulse Space, so they're still working through some commissioning tasks for us. So they were able to get us a heartbeat, so like payloads on, and letting us know it's alive. I'm told probably 2 weeks at this point before we get this thing turned on and fully deploy its little launch locks and, start performing our tests, vibrating a little dummy mass in little circular patterns.
Okay. And is it enough mass that's going to affect Impulse's spacecraft? Is that how you're measuring it?
That'll be rough. And I know you have probably mostly audio listeners, but I have the actual, all right, hold on, let me turn my background off. There we go.
Beautiful.
This is Cicada. This is what's actually up on orbit. I have some of the design of our flexures is a little hidden because that's kind of the secret sauce. We're already a couple revs past this at this point, but yeah, this is bolted to the side of the Impulse Mira satellite, which is massive compared to this payload. I don't know if you saw the picture of the launch vehicle, but
I did see yours on there.
Yeah, we're a little guy. So we will show up as a disturbance in their attitude control system, likely. But the odds that we're able to meaningfully rotate their satellite with such a small mass is unlikely. But they've agreed to, say, hey, look, our reaction wheels spun up a little bit to counteract that disturbance you imparted. So that's the goal. The main benefit of this is to what our engineers call the transfer function. We want to calculate the transfer function of how this thing actually behaves in a zero-G environment with no friction and nothing fighting it. Like, how does it resonate? How do the control commands translate into vibrations and resonance and everything? So that's going to be the real goal here.
And is that gating any progress towards getting Hummingbird ready, or are you doing that in parallel?
We're doing it in parallel. So we'll use lessons learned, of course. But right now we're building out our ground unit of Hummingbird to give us a sort of a demonstration that'll, be able, we hang it from the ceiling on a string and allow it to rotate in one dimension and stuff like that.
Still actually move like a live demo. Oh, that's awesome. Do you have a customer plan for the first mission? Are you planning to fly a customer? I know you had some contracts with SpaceWorks and NASA. I don't know if those were meant to be that kind of role.
We have multiple potential customers to fly as a hosted payload on our first Hummingbird. Can't really disclose who they are, but there's, I think right now, 40 kilograms of payload space to allocate. So we're August 1st is going to be the hard cutoff for any customers to join. So we'll need designs and everything and basically do a design freeze at that point. We're happy to fly people with a slightly higher, risk profile, of course. Any person is going to be a little riskier than the 10.
So you're still looking for customers. So our audience should send in applications.
Yeah. So
any particular customers you're looking for?
No, preferably a payload that doesn't have the potential to explode or, minimizes our risk. But
like an optical payload, would that, benefit you in proving out some of the applications that you're most interested in?
Good. We have again, I wish I could tell you guys more. We have a team at NASA actually interested in flying one of the next flagship observatory payloads on our satellite because we are the only ones really addressing that stability issue. So that's one we are very excited about.
Awesome.
That's huge. So the raise gets your first Hummingbird in orbit. It takes you through a runway of 24 months, 18 months.
Yeah, it's like 16 to 18, depending on how willy-nilly we want to start burning cash. We're targeting hiring 20 to 21 people, but we actually, we might, increase that to 22, 24.
Sure.
Sure. Because we're going after another raise well before we run out of runway. So there's always room to go faster.
Awesome. So you've got all the rope you need in order to get the Hummingbird up on orbit, achieve revenues from your first customer, from your first payload. That's fabulous. So I'd love to ask you some questions and better understand sort of the I'll say the marketing strategy, sort of your go-to-market plan, whether you're looking more at commercial, government, or defense applications, like NASA. I would consider sort of federal and government, though I would certainly consider NASA to be a different beast than selling into AFWorks or SpaceWorks or anything out of DoD or DoW. So tell us a little bit about how you're sort of viewing your current, or I'll say beachhead market, and then your additional sort of markets therefrom. How are you planning on sort of growing and sinking and sinking the next couple of putts here?
Yeah. So if you asked me a year ago, I I would have said our beachhead market, and it still is optics. Earth observation seems to be making a little bit of a comeback, which is nice, and optical comms are just becoming more and more the standard in orbit. So our beachhead are customers that want to fly either or both of those payloads for sure, but we recognize that the satellite bus market is getting competitive. Has been competitive for a couple of years, and there's more and more people switching, like traditional companies starting to sell their own hardware. So what's always been the goal is to eventually operate our own satellites. We're just sort of bringing that goal into the present a little more quickly.
Are you trying to pursue contracts globally? Or are you focused on the U.S.?
It'll be U.S. first. The U.S. DoD is the obvious. Anyone in space not going after those contracts, it seems like you're just not going to make it nowadays. But of course, our allied nations, we're happy to engage with them as well.
Fascinating.
Awesome. Did you guys get qualified under the MDA Shield IDIQ?
No, at least not yet.
Gotcha.
This is new. Step one is still like, let's build Hummingbird. Step two is let's retrofit it with these antennas and start getting some demonstrations. So we're likely to put an initial tech demo of this on our 2027 mission, but it's not going to be the full 10 or 12 meter wingspan that we're looking for that big RF aperture.
Very cool.
That's awesome. Well, so tell us a little bit more about yourself and Vedant. So the two of you met in grad school in Illinois, and this was, if memory serves, this was Urbana-Champaign campus, correct?
Yeah.
Awesome. Well, so tell us a little bit about your backgrounds, and Samara Aerospace has been sort of pedal to the metal, executing and absolutely crushing it for as long as I've known you, for sure. And so, like, just help us in the audience understand exactly why you and Vedant and the team at Samara Aerospace are so damn qualified to execute on everything that you've been doing.
Yeah, I'm not good at talking about myself. I'm pretty modest. I have no problem telling you why Vedant is just absolutely crushing it. That guy, I've always said, is just the smartest person I know. He's frustratingly intelligent. Any system he doesn't know about, he just goes out, he reads the book and becomes the expert. So I have no doubt that with enough capital and time, this guy could just build the entire satellite himself. He's just this brilliant engineer that fundamentally changed the way satellites are moved in space, or not moved, rotated. And I just happen to be a good friend of his. I'm also an engineer. I am qualified. I've built satellites. I've developed satellite technology for well over a decade. But it was mostly like, hey, I'm willing to put in the time. This is super cool. I see the immense potential of this system, and that's why we said, okay, I'll manage the business. I'll make this thing happen. I'll keep you funded. You go develop these game-changing technologies in this next generation satellite in the lab. That's kind of it in a nutshell. We're just sort of two friends that set out to do something really cool and fun together.
Man, I wonder what that's like. Well, so this is why we got to have both of you on the show, so that you can tell us about all of Vedant's accomplishments and his achievements, and that he can do the same for you.
Well, he wouldn't do it for me.
You downplayed it a lot. I mean, when you're not kidding, over a decade of experience, but all in GNC, like, you know your stuff when it comes to this field. And I'm really curious to hear, like, 10 years of working on the Blue Canyon's a well-respected controls company, and you had 7 years at CUA working on, like, GNC solutions. So have you ever come across a problem that you don't think what you're working on now could solve, or is this really a culmination of your experience?
No, it's kind of unrelated to the problems I was solving. Let's be clear. I mean, I was a software engineer for half of that time, creating trajectory optimization algorithms for NASA. So nothing to do with GNC. Well, nothing to do with additive. Yeah, so it helps that I have a fundamental, like I can write out the equations of motion. I understand fundamentally why this is important, and I've talked to all the engineers dealing with these problems and know, like, deep when you go beyond the systems engineering level and you talk to the people in the weeds solving these problems on orbit, you realize, oh wow, we are solving something. It's not front page news, but it's something all of these engineers building these satellites are actually dealing with. And that's, jitter and stability. It's just everybody has assumed for 50 years that there's only one solution. You got to put spinning wheels on your satellite, so design around that. And now we're trying to reach out and convince these people, like, hey, there's another way, and think about things you can do.
Yeah, it's kind of a radical shift in how things are done. And I've had this feeling that we're underselling like how different this is compared to anything. Because you're right, there aren't any analogs to this. Like there have been crazy control schemes in the past, like gravity gradient, giant momentum wheels. Like there's been other controls, but what you're proposing is when I keep hearing it, it's almost too good to be true. The fact that you can control the attitude, you can do it stably, you can do it quickly. Like, I guess going back to my initial question, like, is there anything this thing can't do? Are you really designing like something that just completely shifts how we do everything?
Yeah, and I want to be clear that there's some downsides, but yeah, it does sound it sounds far-fetched and too good to be true. All new technology does. But what convinced me is like I got to spend I think 2 years just sitting with Vedant trying to poke holes in it and convincing him why this isn't commercially viable and it's an academic problem. And every step of the way, he's like, "Oh no, I solved that." And here's why this is easy, and here's how you make it survive launch, and all these other problems. But I went down a rabbit hole just now. I forgot your initial question.
Like, I don't know. I want to kind of get to. I'm trying to find a way to capture like the tech that you've done, because it's really hard to just explain. Like it can do anything. Like you just mentioned, like launch loads were one of the things that popped in my head. Like, can you talk about how you solved that?
Yes, I mean you have to lock down these flexures. So we are using it's no secret piezoelectric crystals that expand and contract very, very slightly, but with a tremendous amount of force. And we've developed custom flexures that wrap around that and sort of amplify that motion. So you get a trade-off. It's a lever arm, basically. Yeah. You get more displacement with less force out of those actuators. So some of the downsides, it's not off the shelf. Reaction wheels are off the shelf. Any satellite can go to Blue Canyon and you can bolt 4 other wheels anywhere on your satellite in the correct orientation. It's plug and play, no big deal. Ours, you have to know the solar panel. You have to design a system specifically for that solar panel and that satellite, and hinges that are this far apart, etc. So that's one downside, and that's why we're building the whole satellite bus and not just selling a component.
Yeah. And the other 6 degrees of freedom control.
Yeah. Yeah, it's sorry. No. I answered that confidently. Each panel has 4 degrees of freedom and has 4 actuators.
Oh, okay.
We are purely rotation. So we can rotate the satellite. We can't do the 3 translational degrees of motion, if that's what you're referring to.
Yeah.
Well, all right. So I misspoke. You can do like millimeter bumps back and forth if you're doing like advanced proximity ops and docking or something, and you need to jerk the panel out to one side. You can bump the rest of the satellite off to the left. So that's something you technically can do. The other downside, I would say, just because it's important to let people know this isn't a purely miraculous, God system. The peak slew rate is probably going to be lower than if you put some giant reaction wheels on your satellite. But where we make it up in agility is our ability to use a tremendous amount of torque to reach our peak slew rate almost instantaneously, and then we stop on a dime. Other people, it's a slow ramp up to a higher rate, a slow ramp down, and then you sit there waiting for your satellite to stop fluttering and wobbling, and then you can take your picture or whatever. Us, it's just boop, 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 done. You're good. Active stabilization the whole way.
And
So
is there anything preventing the customer from adding control systems? Like if they wanted to put a reaction wheel in the payload area?
Not at all. Yeah. The initial system was designed to fly in tandem. Initial back in like grad school during its development was going to fly in tandem with reaction wheels, purely to cancel out the instability caused by said wheels. And then Vedant had this sort of aha moment where he's like, oh, if I'm clever about how I vibrate the panels, I can also rotate the satellite while canceling the jitter.
Okay, so it is capable of remaining stable as it's slewing.
Yeah. When during a slew, you'll probably see an increase in jitter throughout the satellite just because you're trying to do two very different things at the same time. But yeah. But to answer your other question, if a satellite really needs to spin up really fast, you could toss reaction wheels on as a payload as well.
And given that it's on the solar array and you have to point the solar rays to the sun, is there any sort of restriction as to how much you're able to kind of point them for beta angles, or if they're pointed, do you lose some controllability?
No. So those two things should be entirely separate. We're not currently planning on flying SATOs to articulate the panels or rotate the panels like some satellites do. The displacements we're talking about here, the millimeter scale. Well, like this is a vibration of the panels. They're never going to be pitched or tilted in such a way that you're going to lose sunlight because it's actuating. If that makes sense.
Yeah.
And then as an R&D project is to develop a SATA that is stiff enough to transmit the vibrations we need through it without ringing in the gears, which it would on like off-the-shelf SATAs on the market right now. But that's a future problem.
Awesome. And does this work with any solar array? You said there was some limitation there.
No. We're thinking about different form factors and everything, but it really helps us to have very rigid traditional solar arrays. And in some cases, the heavier, the better. So like if you have cheap solar cells ready to go, supply chain's not an issue, but they're heavier, that actually gives us a benefit. We get more control the heavier the panels are. We've even toyed with the idea of putting our batteries in the solar panels. You would never get that in traditional design, but it's like, okay, wait, hold on. That would give us a control advantage. Now that is a thermal nightmare that we'd have to solve. So again, future R&D project, but these are the things we're excited about. We're like, wow, there's so many new cool things you can do with the satellite when you change this fundamental way it's developed.
Yeah. It's really awesome.
Thermal engineers are pretty smart. They'll be able to solve those problems.
It's fine.
You don't want to sunbathe your batteries, though. That's generally not great.
I'm sure you'll come up with a battery that can handle it. It's too cool an idea not to figure out, honestly.
Yeah.
So, Pat, tell me and Harrison here, tell us about sort of your and Vedant's journey to the two of you and your journey to becoming founders and what that experience has been like. You both come from the industry. You both come from engineering. You're both sharp as a tack in what you do. Tell us a little bit about how you wound up deciding, hey, you know what? Let's go ahead and start a space company together.
Yeah. Reckless optimism. That's kind of what it boils down to. No, yeah, it was, two people who understand the problem, saying this should exist, and the only way it's going to exist is if we do it ourselves. For Vedant, by all means, this guy's job is extremely difficult, as we all know. But he got to keep doing his job, which is be an amazing engineer and keep developing this thing. I had to do a bit of a pivot. I had no business starting a business back when I did in 2022 is when we officially incorporated purely to apply for SBIR funding in our free time and go to conferences, and spent like 2 years just burning all my vacation time at my day job, going to conferences and reading books and trying to learn business 101 that I would have known had I gone to business school, and just sort of putting in the work to become somebody capable of, running this company and selling this product. I won't claim to be amazing at explaining this technology, but oh my God, you should have heard me try to explain it in 2020. So yeah, the founder journey was just like, I have a lot of work. I have a lot of personal growth that needs to happen to run this business. And I love it. That's what motivates me, is just always growing as a person, seeing definitive progress along the way. I barely, my former self from 3 or 4 years ago wouldn't even recognize me today, but in a good way.
Very nice. Well, congratulations. We'd love to hear that, and it's clearly working. Everything that you and Vedant are putting into Samara Aerospace is clearly coming out the other side nails. So wonderfully done. Additionally, I wanted to sort of chat with you here. I mean, we're reaching the end. I mean, so you've closed this wonderful seed round. You're looking at leveraging the capital, growing rapidly, getting the Hummingbird up, getting the demo up, and proceeding forward into a Series A raise. So, what are you most excited about in this sort of like next phase of Samara Aerospace, and like what gives you the most agita? What gives you the hardest time, keeps you up at night, sort of thing? What are you most excited about and most worried about?
Yeah, I'm excited to just start getting this thing built out on the ground, even if it's not in space yet. Seeing the Hummingbird in the lab, even if the guts aren't all in it yet, built out, the panels deployed, hanging from a ceiling on the mass offload system we're developing, and all that stuff. So that's what I'm really excited about. Having enough capital in the bank to move forward and sort of stop cutting corners the way startups do, and we're still scrappy. We still make things happen with, the resources available, but it's nice to be able to buy, the TVAC chamber that we need to run all our tests and everything, and build out the facilities and get the team that we, want in-house right now. So that's what excites me. What keeps me up at night, I mean, the cheap answer is the same as any startup, is, money. It's like, okay, money's not a problem right now, but who knows? In 12 months, maybe it'll be. Maybe something will happen with the economy, which seems to be chaotic and uncertain right now, that changes things. Right now, it's looking like a great year to fundraise, but nowadays, all that can be changed with a tweet. So hopefully everything stays where it's at. Hopefully the SBIR reauthorization comes through, and we can go for a Strat Fi this year. But right now, that's completely offline. So just a little politically dicey right now.
Sure. I mean, I would imagine that for most founders, like the Serenity Prayer isn't the most applicable. I would imagine that like it's it's vastly more preferable to be in a situation where the only worries are the things outside of your control, because you've already solved and accomplished and knocked out of the park everything that is effectively within one's control. But to your point, very understandable that hey, we're doing a great job. We're not worried about being able to execute on our end. We're worried about some of the tailwinds disappearing, or headwinds that are just outside of our control materializing. But makes perfect sense, and best of luck in anything there. So we've got a little bit of time here. So Pat, who do you need? What are you looking for? How can we or our listeners be the biggest help to you and to Samara Aerospace?
That's a tough one right now. It's always, you just brought in capital. Hiring is, we put a lot of time and effort into interviewing and finding the right people for the job. There are some niche places in satellite development where the pool of candidates is a little shallower. So specifically, we're looking for embedded software engineers, programming microcontrollers and whatnot, people experienced in satellite thermal analysis is another big area. But in general, it's mostly engineers coming our way. So mechanical, electrical, and software, hit us up, check out our career page.
Just want to say thanks again for joining us. It was an awesome conversation. I think your technology is so cool. I can't wait to see it fly on your first Hummingbird.
Yeah, thanks for having me. Appreciate it. Hopefully I didn't ramble too much.
No, we love a good ramble.
Yeah, that's what
You didn't
this is
ramble
for.
Pat, thank you so much for showing up. It's been great chatting with you and catching up, and great to share with our listeners everything that you've been working on. Huge accomplishments. Congratulations again to you and the team. And we're happy to host you anytime you want to come on and tell us about some of the new stuff that you're working on, or some of the big updates or big announcements that you have. In the meantime, anybody interested in getting in contact with Patrick and the team here at Samara Aerospace would be best served reaching out to?
Probably, I think we have a contact form on our website, but info@samaraerospace.com is always the easiest sort of general interest form. And then, of course, we have jobs@samaraerospace.com if you have a job related question, and maybe one of the open applications isn't directly your field and you want to talk about joining the team, we're happy to have you reach out that way too.
Wonderful. Well, thank you so much, and we appreciate your time.
Yeah, likewise. Thanks, guys.